Welcome to this video. Today we'll be looking at algebraic operations on vectors. Some of the prior knowledge that you may need include magnitudes of vectors, unit vector representation, component form of a vector, and geometric operations. First, we're going to focus on addition of vectors. So let's assume that we got vector A with components ax and ay, and vector B with components bx and by. When we add the two vectors, if we were to draw them, we would draw A with its x component and y component, and vector B with its x and y components. Our resultant is from the initial point or the tail of A all the way to the head of vector B. So now we're going to draw the x components of our resultant vector, vector A plus B, and we can see that the x component of this is the x component of vector A plus x component of vector B, and the y component of this vector is the y component of vector A plus y component of vector B. Therefore, whenever we're adding two vectors, to get the x component of the resultant vector, we add the x component of the individual vectors. And if we want to get the y components, we add the y component of the individual vectors. Note that this can also be written in the unit vector form, where the x components correspond to the unit I vector and the y components correspond to the unit j vector. Here's a very quick example. Vector A has x and y components of 3 and negative 4, and B has x and y components of 4 and negative 8. And if we add the two vectors, we add the individual x components of the two vectors, 3 plus 4 for x, and negative 4 and negative 8 for y, giving us a final answer of 7 as our x components and negative 12 as our y components. Let's look at negative vectors here. We're going to look through an example of a position vector A, which originates at point 0 and terminates at point 3, 1. A negative vector to this will have the same magnitude, but it will go in the opposite direction, terminating at point negative 3, negative 1. Therefore, this vector, which is negative A, will have an x component which is negative 3, negative to the original one, and negative 1 as a y component, which is negative of the original vector as well. So in general, if vector A has x component of ax and y component of ay, then negative A will have an x component which is negative ax and a y component which is negative ay. Now, how do we algebraically subtract two vectors? Well, if we add vector A minus vector B, then that's same as writing vector A plus negative B. So then we can write each component as ax plus negative bx, which is ax minus bx, and ay minus negative by, which is similar to ay minus by. So to subtract two vectors, we simply subtract their x components to get the x component of the resultant value and their y components to get the y component. Let's do a simple example. Vector A has components 3, 5, and B has components negative 4 and 2. So if we want to do A minus B, then it will become the x component of A, which is 3, minus the x component of B, which is negative 4. So 3 minus negative 4 will give us 1, and we do the same thing to get the y component. So the y component of vector A is 5, and we subtract that by the y component of vector B, which is 2, and 5 minus 2 will give us 3. Note that A minus B does not always give us B minus A. In this case, B minus A is negative 4 minus 3 for our x component, and 2 minus 5 for our y components, giving us negative 7, negative 3 as our final answer. To multiply a vector by a scalar value, meaning a value which is just a number but not a vector, we'll learn how to multiply vectors later. Let's assume that we got vector A components 2 and 1. 3 times A means 2, 1 plus 2, 1 plus 2, 1. Because there's 3 2's, that's 3 times 2 for our x component, and because there are 3 1's, that means 3 times 1 for our y components, giving us 6, 3 as our final answer. In general, when we multiply a scalar value k by a vector A, which has x component of ax and y component of ay. This will give us k times ax as our x component and k times ay as our y component. For example, if we were to multiply -8 by our vector a, -8 times 2 will give us the x component as -16, and -8 times 1 will give us the y component as -8. And obviously we can write this in the unit vector form as well. Here's a short summary of all the concepts that are covered, so you can pause and write them down. And now we're going to look at an example. In this example, we are going to be given two vectors and we are going to calculate their addition, so vector a plus vector b. We are then going to look at 3a minus b and the magnitude of vector b minus 2a. For part A here, we got vector a, which has x component of -4 and y component of 4. And we want to add vector b, and vector b has x component of 3 and y component of 2. So we simply add those numbers to get an x component of 2 and y component of 6 as our final answer. For part B, we got 3 times vector a minus vector b, so that's 3 times the x component of a, which is -1, and 3 times y component, which is 4, and we're subtracting that from vector b, so 3 as x component, 2 as y component, and that becomes -3 minus 3 and 12 minus 2, which is equivalent to -6 for the x component and +10 for the y component. For part C of the question, we're looking at vector b minus vector a multiplied by 2. So we'll do that first before we find the magnitude. That's 3 to minus 2 times x component of a, which is -1, and y component, which is 4. That is equal to 3 minus -2, which is same as 3 plus 2, and 2 minus 2 times 4, which is 8. And 3 plus 2 is 5, and 2 minus 8 is -6. Now for the magnitude, we will use the square root of the x component squared, 5 squared plus -6 squared, which is the y component squared, and that's 25 plus 36, giving us the square root of 61 as our final answer. We can write that in 3 significant figures if we're in the IB program, and that's 7.81 units. I've left you with a practice question, so you can pause and write it down. I will try to post up the solution to this as soon as I can in a separate video. I hope that this video helped you with understanding two-dimensional algebraic operations, and thank you for watching.